Hello everyone, my name is RauSimple. Welcome to the next tutorial. So today we are going to discuss week 3 assignments of Andro-NG. So in this particular exercise, all the exercise will be based on the logistic regressions, and this has all this exercise which we need to complete: the plot data.m, sigmoid.m, cost function.m, and predict and cost functions regularization. Okay, so coming to the first one, which is nothing but the plotting the data. So in plotting the data, we just want to plot the data, that's all, nothing else. So if I can show you the vectorized implementation of plotting the data. So in plotting the data, what we are doing, there is a feature, we are passing the feature. Basically this data set has two rows, data set has two feature, marks 1 feature, marks 2 feature, and it has one output. And the output, obviously it is a logistic regression, so it will have only two labels, either 0 or 1, right? Either positive or negative example, because it has binary classifications. So we are just going to find if y is equal to 1, we are taking that as a positive example. If y is equal to 0, we are taking that as a negative example, and we are just plotting the plotting x feature 1. This is the feature 1, feature 1, all the feature 1 which are positive, and here all the feature second which are positive with the sign, and we are giving the symbol as a plus to represent. And similarly we are representing the negative example x, and all the negative examples of feature 1 and all the negative example of feature second with the mark O. So this is what the diagram you will get. Once we'll draw, we'll get the diagram like this. So all the positive with the plus and all the negative with the 0. Now coming to the next one, the next one is this sigmoid.m. Now before going to this, I just want to give a brief introduction about what basically are logistic regressions and why we use this sigmoid function in logistic regression. So the thing is, if you remember, in linear regression, the equation of straight line, right? The equation of straight line can be written as y is equal to mx plus c. So this is what the hypothesis. So basically the hypothesis which we are considering for linear regression, what theta transpose x. Why theta transpose x? Because if it has multiple feature, it will become m1 x1 plus m2 x2 and so on plus c. Okay, and this complete, if you replace m1 as a theta 1, m2 as a theta 2, so this complete thing can be written as a theta transpose x, where x is nothing but a matrix of all the features, 1 2 3, whatever the feature we have, it will be a matrix for all feature. But in logistic regression, so if you see in linear regression, this can compute the values from anything, any values it will compute, either 0 1 2 3 4, whatever the value, it can compute any values, right? The line can extend top and bottom, so it can predict in. But in logistic regression, we always want our values to be between 0 and 1. So in order to get the values between 0 to 1, we are going to pass this straight line equation with a sigmoid in a sigmoid functions. So we are going to just pass this straight line equation in a sigmoid. Suppose if I consider this as a z is equal to theta transpose x, so we are going to pass this z into a sigmoid function, and sigmoid function is nothing but 1 plus e power minus z. Okay, so basically what basically it will become 1 plus e power minus theta transpose x. So this is what the hypothesis which we are going to consider in our logistic regressions. Okay, so in linear regression this was the hypothesis, but in logistic regression the hypothesis is 1 by 1 plus e power minus theta transpose x. Why we are passing it to sigmoid function? Because we want our values to be light between 0 to 1. So that's the reason we are passing. And if I'll show you the diagram for this sigmoid function, so this is the diagram for sigmoid functions. So this, so if you see, it's always written the values between 0 and 1. This is 1 and this will be 0, so it's always written the value between 0 to 1, and we can set some threshold, like when the values predicted by this sigmoid function, if it is greater than 0.5, we say it as a positive example, and if the value is predicted less than 0.5, you say it is a negative example. So this is the thing. So now we understood why we use sigmoid function. Now coming to the vectorized implementation of sigmoid.m. So what we are going to do, we are just passing that z is nothing but here theta transpose x, and then what we are doing, we are just initializing that sigmoid as a sigmoid function as a 0 of size z. Okay, like obviously it will have a size of z. So the size of z, as it was a matrix theta transpose x, it's a matrix, so size can be. So on the basis of that we'll just declare g. Okay, because if there will be multiple feature, we'll get multiple g. Now g is equal to 1 by this value, what I have written just now, that is 1 by 1 plus e power minus z, 1 by 1 plus e power minus z, right? So you'll write the same thing, 1 by 1 plus e power minus z. Exponent of minus z is nothing but e power minus z. And why we are writing dot here? Because we want to do this operation for all the things, like for all the features, right? For all the features, because it is a vectorized implementation. So there might be a possibility there will be multiple features. So when there will be multiple feature, we want to do this sigmoid values, or you want to find the sigmoid value for multiple feature. So that's the reason we are writing one dot. Okay, so this is the sigmoid implementation. Now coming to the next, that is cost function dot m. Okay, so before coming to the again cost functions, I just want to explain what will be the cost function for this logistic regression, right? So as we know, in linear regression, this was the cost functions, right? In linear regression, the cost function was nothing but what it was. If I can write the cost function for linear regression, it was 1 by 2m summation of I is equal to 1 to m, and here h theta, this was the hypothesis for linear regressions, into y whole square. Now the problem here is I can write also this as a 1 by 1 by m, and then I can write it as a summation of I is equal to 1 to m and 1 by 2 and h theta minus y whole square. Now the problem here is, if I'll use this, as we know here the h theta in logistic regression, the h theta is nothing but what, 1 by 1 plus e power minus theta transpose x. So if I'll use there, it will then the diagram will be like kind of this. So there will be multiple local minima. So there might be a possibility that will not be able to converge to the local minima. So in order to avoid this, we want our graph should be like this, right? Such that we can reach the global minima easily. So in order to minimize that, in logistic regression, we are not going to use this as a cost function. Okay, in cost functions we are not going to use this. So in place of this, we are going to consider the cost functions, like this value will be equal to, suppose if this value is something I can consider as a, let's consider capital X. So this capital X should be equal to minus log h theta of x, that is hypothesis, if y is equal to 1, and then minus log 1 minus h theta of x if y is equal to 0. So the thing is, we are not going to use this value in a cost function for logistic regressions. Why? Because it cannot guarantee to converge to the global minima. So in order to converge to the global minima, we want our graph should be like this, that is the convex graph. So we want our graph should be like this. So to minimize so in order to get this kind of graph, we are just going to replace this value with this, that minus of log h theta of x if y is equal to 1, and minus log 1 minus hx if y is equal to 0. Now the combined, so instead of this, when I'll place this, and one more thing, this two value together, what I can write as a minus y, this x can be written as minus y log hypothesis h theta of x minus of 1 minus y log 1 minus h theta of x. So I can write this x as a this. Okay, if you substitute y is equal to 1 here, if you substitute y is equal to 1, you'll be getting this, and if you substitute y is equal to 0, substitute y 0, so if you substitute y 0, this becomes 0, and if you substitute 0, this becomes just 1 into this, so which will give you this value, right? So this together can be written like this. Now just replace this value to in this equation, that is 1 by m instead of this. So now what will be our cost function here, j theta for logistic regression? So it will be 1 by m, this value 1 by m, just take minus common here, so 1 is minus 1 is, and it will be remaining y log h theta of x minus of 1 minus y log, sorry, it will become plus, right? So when we are taking this minus common, it will become plus 1 minus y log of 1 minus h theta of x. Okay, so we have just taken minus as a common, so it will become plus. Now this is the cost function for logistic regression. So once again I'll repeat why we are using this as a cost function. Because in linear regression, if I'll use the cost function which we use in linear regression, this is basically the square error, right? So if I'll use this for logistic regression also, what will happen, there might be a possibility that our algorithm will not converge to the global minima. So in order to avoid that, as we want our graph should be convex, so in order to avoid that, in place of this we are going to use these values as a cost functions. So when you use this and the combined, the two can be written like this, and finally the cost function will be minus 1 by m. So this will be our cost function for logistic regression. Now again, after getting this cost functions, what is our next agenda? So our obviously the next agenda is to minimize the value, right? What we want basically obviously we use gradient descent here. So again, theta is equal to theta minus and partial derivative of this cost functions with respect to theta, right? We want to do that, and here there will be alpha. So we'll use this itself, that is gradient descent, in order to optimize this cost function. So that is theta is equal to theta minus alpha and partial derivative of j theta with respect to theta, right? Now when we are going to differentiate this, so obviously we want the differentiation term here, right? That is differentiation of j theta with respect to theta. So we want partial derivative of j theta with respect to theta. I'm not going to differentiate this. So in order to differentiate, but I'll just tell what how we can differentiate this. So in order to differentiate this, just replace this h theta with 1 by, obviously we know our h theta, our hypothesis for logistic regression is 1 by 1 plus e power minus theta transpose x, right? So this is, so log this 1 minus y log 1 minus 1 by, and then we need to differentiate and make sure as we are doing the partial derivative. So when we are doing the partial derivative, so only with respect to what, like suppose if you are differentiating with respect to theta, so only theta will be considered as a variable and the remaining everything will be considered as a constant. So considering everything as a constant, we'll just differentiate this differentiation of cost function, and finally what we'll get after differentiation, we'll get 1 by m summation of I is equal to 1 to m, and here we'll get h theta of x minus y into x I j here. This is nothing but x I j y because for all feature sets. Okay, so this is the thing. Xi is nothing but adding all the example, and this xj for like for feature 1, if it is a multivariant, we'll get all the features x1, x2, x3 kind of this. So this is similar to the linear regression. So after differentiation we'll get this. So that now coming to this octave. So here j is nothing but the differentiation. This itself in octave implementer we are writing this as a j. Okay, so this as a j and this as a cost function. So now in octave implementer, if you say this initially we have written j is 0 and gradient we have written zeros of this. Okay, now coming to the this. So what we want, obviously we want our cost function j. So the cost function j is nothing but what, 1 by m. So this 1 by m minus, if you can take it inside also no problem. So 1 by m minus y log this hypothesis. So we have written 1 by m into summation, obviously summation is there, minus y into log hypothesis. This h of x is nothing but what, sigmoid of z, right? Because it was 1 plus e power minus theta z, right? 1 by 1 plus e power minus theta z, and z is nothing but theta into x into theta. So z is x into theta, and then h of x is sigmoid of z. So that is our hypothesis. So log h of x minus 1 minus y into log 1 minus h of x. So exactly the same what we got here, the same values we have replaced. So this minus the theta transpose x is nothing but the z value, this is z, and then this z we are passing to the sigmoid. So and that will be our hypothesis, right? So that is our hypothesis, z, then passing to the sigmoid, and that is our hypothesis. So this is the j value. Now coming to the gradients. Sorry, here one mistake. So this is not j, this is the gradient we have considered in the octave. So this is the gradient. So what we got, 1 by m summation y is equal to 1 to m h theta of x minus y into xj, right? So this is what we want to write, 1 by m and then h theta of x minus y. And why we are writing here x transpose? Because as I told in my previous tutorial, in order to make it multiplication possible, so the multiplication is possible only when the order of the two matrix matches, like the column of the column of first matrix should be equal to the row of second matrix. So this, and then we'll do this. So after getting this will be the gradient. So This is the things. So this is what the implementation of your cost function. What and all we did, we just find the cost function and then the differentiation of this cost function, which I showed here, right? So I hope it's clear to everyone. So that's all about today. If you have any doubt regarding this particular topic, so you can comment down below. I'll be happy to answer. And the remaining, I'll be going to make a part second. In that, I'll explain the remaining part. So if you like this channel, please like, share and subscribe. Thank you.